All right, we'll go ahead and get started here. Something happened to our projector. That's way higher than normal. I have to fiddle with it, break it. It's up too high. All right. So I'll start with some quiz questions. Didn't get through all of them because I have 2 weeks worth of quiz questions to answer, but most relevant ones are on here. Are combustion reactions the only reactions that create water and carbon dioxide? No, but they're the most common reaction to create both of them. Lots of reactions create carbon dioxide, lots of reactions create water, but combustion is by far the most common that does both of those things in the same reaction. There are other reactions out there that can make CO2 and water. For instance, your classic baking soda volcano is acetic acid plus sodium bicarbonate, and it reacts and it makes carbonic acid and sodium acetate. But when you have carbonic acid in too high of a concentration, so you start by making, here's our carbonic acid, H2CO3, and sodium acetate. And everybody, of course, remembers the formula for acetate now that we've had our polyatomic ion quiz, right? After it survived Thanksgiving, it's now permanently etched in your brain, right? This doesn't really do anything. These are spectator ions. We're writing the net ionic equation. They wouldn't really play much of a role. But if you have too much carbonic acid dissolved in water, it actually will split up into CO2 molecule and a water molecule. So this one further reacts to make H2O as a liquid and CO2 as a gas. That's already balanced too, right? Because you just take one of the oxygens from the carbonate and the 2 hydrogens that are balancing out the charge, and you get an H2O. So this is actually what's happening when you add baking soda to vinegar. It's doing this. This is why it foams up, because you're making CO2. You're also making water. So this is another example. This is not a combustion reaction. It's still making both of these. So like 2 reactions sequentially to do it. But this also what's happening when you open up a carbonated beverage. That foaming is basically when you carbonate something, you're forcing extra CO2 to be dissolved in the water, which turns it into this form. When you remove that extra pressure by opening it, you can start producing CO2 again. We'll talk about pressure in gases today, and solutions for that matter in the next second. So this is actually relevant to what we're going to talk about down here. But it's, the carbonic acid is one of the reasons why carbonated beverages taste more tart, why they have a little bit of a bite to them. Even if it's just water, it is more acidic. It has a lower pH because the act of carbonating makes it more acidic because you're making this.
So is cellular respiration a combustion reaction?
If you look at the net result of cellular respiration, yes. Because combustion is really specifically saying we're something carbon-based that we're fully oxidizing using oxygen. The net result of cellular respiration is the same as just plain out burning sugar. The difference is that our cells are only really able to make one other high energy molecule per reaction. And so if you burned all of that at once, you'd only be making 1 ATP or 1 NADH per sugar molecule. But if you break it up into a bunch of small steps that are all individually downhill in energy, you can make a whole bunch of NADH, even though it's the same net result. It's the equivalent of putting one big hydroelectric dam on a river versus a bunch of small hydroelectric dams along the river. You can actually generate more current or more electricity if you do it in a bunch of small steps rather than one big step.
I thought about it in terms of selling like an ounce of weed to someone instead of a pound.
yeah, more small transactions are going to be more profitable generally, yes. That is also a valid analogy. Can combustion reactions only occur with oxygen present? Yes. If you have a bunch of carbon-based molecules subject to a lot of heat and pressure without oxygen present, you get fossil fuels. So that's actually where fossil fuels come from, is the fact that they were buried under the earth where there was no exposure to oxygen. They couldn't be fully oxygenated, or sorry, oxidized, because there was no oxygen around. So they just kind of sat there and stewed and stayed with lots of carbon-carbon bonds and carbon-hydrogen bonds. So all we're doing now is we're completing, when we burn fossil fuels, we're completing that oxidation process that started when the animals died, or animals or algae or whatever. I think most fossil fuels are actually algae if you look statistically, which is not as cool as saying we're burning dinosaur bones, but it's more accurate. So combustion reactions, if you don't have oxygen present, things won't burn, which is why flames go out if you suffocate them. If you just deprive them of air, once they use up the oxygen, that turns oxygen into the limiting reactant, and the reaction stops. We don't think of oxygen in a combustion reaction as being the limiting reactant because we're used to being in an atmosphere that has lots of oxygen in it. But it absolutely will happen under the right conditions. This one's less relevant to what we're talking about, but it's worth talking. I don't even know. I think this is less of a debate these days. I think the same people that were up in arms about fluoridation are now up in arms about GMO stuff and things of that nature. And fluoridation is less controversial. It shouldn't be controversial at all, though. It's really, really well established and safe. I think it was controversial for a bit because there was a study in 1990 that showed there might be a correlation between a certain form of bone cancer and fluoridation of water. But it was shown to be very, very robustly shown to be a statistical anomaly. That study got published. They didn't do anything wrong. They just happened to get really unlucky with their numbers and had too small a sample size. So when they tried to replicate that study, they found out, oh no, that was just random noise. That was just this group of people was unlucky when it came to bone cancer. So other than that, there's really nothing. If you get to really extremely high levels of fluoridation, it can cause problems with osteoarthritis and bone density issues. But that's at way higher than what we actually put in water intentionally. And actually, in the US, water treatment plants remove excess fluoride in areas that actually have too much fluoride. So it really should not be an issue because it is pretty much agreed universally. There might even be greater consensus among scientists and doctors about fluoridation than global warming. So if that gives you any sort of indication as to whether or not it should really be a debate, it shouldn't be. And that's all I'm going to say about that. So you guys are going to get into phase change and spend a fair bit of time on phase change next quarter. But it is actually really cool stuff and something we have experienced every day when it comes to phase changes of water. So it's worth spending a couple minutes on here, especially since we're starting to talk about solutions and we'll talk about gases today. Is there a fourth phase of water? And then that's sort of a different than the rest of this question, and I'll explain why in a second. The answer to the first part is yes, but it's not anything to do with an exclusion zone, which is a term I'll talk about, like I said, in a minute. Basically, if you look at any substance, it has what's called a pressure temperature curve, where you basically can divide up, and there's certain conditions you can predict whether something is going to be solid, liquid, or gas based on a combination of pressure and temperature. It turns out it's not just temperature. We just think of it as being mostly due to temperature because we usually are operating under atmospheric pressure. Since we're used to atmospheric pressure being constant, we're basically looking at one slice of this graph, where you can say, okay, as you increase the temperature, you go from solid to liquid and then into gas. But if we vary the pressure, we basically slide this line up and down.
Then you get some weird.
You get some weird things happening.
Yeah, like ice 2.
We'll talk about different phases of solids in a second. But yeah, basically, if you go to a low enough pressure, you can go straight from a solid to a gas, which we call sublimation. If you happen to get just the right pressure and temperature combination, you can have something that's called the triple point, where you can have all three phases present simultaneously at equilibrium. So it's not like you have ice and in a glass of water with some evaporation happening at the same time. It's in if you're at just the right combination of these pressure and temperature. But if you get up here, you get up to high enough pressures and temperatures, you get to what's called supercritical fluid, which is the more accurate name for what used to just be called plasma. So basically, when you get to high enough temperatures and pressures, it behaves like a liquid, but the electrons are not really bound to the nucleus anymore. Electrons kind of freely move around because all of the electrons have enough kinetic energy, they can basically bounce out of those energy levels anytime they want. So when you get up here, you can't have chemical bonding, because chemical bonding is based around having these orbitals that have electrons in them, right? If the electrons can move out of those orbitals anytime they want, then you don't have chemical bonding happening. So basically, when you get up to this area, we're talking about things like the surface of the sun. The sun's not a ball of fire. It's actually a plasma. It's a supercritical fluid, because it has high enough temperatures and pressures that the electrons just move through it, which is kind of cool. So there is absolutely a fourth phase of water, and there's actually about 11 different phases of ice. So there are 11 different crystal structures that at different conditions you can get ice to be in this shape or be in this crystal structure or be in that crystal structure. And so you could even consider those different phases, and then there's a lot of different phases. They're all solids, but it's like the difference between graphite and diamond. Those are two different solid phases of carbon, right? And the only difference between them is that you have to take it to a really high pressure to get it to form into a diamond. You take the same substance and it's going to have another sort of line in here that's going to be where you cross from being coal into being a diamond. Jordan?
Are there any other states of matter besides solid, liquid, gas, and plasma?
Sorry, yes, to get back to this one, there's been some research that says that when you go from a solid, I don't remember if it's a liquid to a solid or a solid to a liquid, or sorry, it's one of these normal transitions where they say basically it's like halfway in between a liquid and it's like evaporation has started but it hasn't finished and kind of behaves a little bit differently than either a liquid or a gas. Actually, I think it was melting. I think it was between a solid and a liquid. I haven't seen enough information to say whether that's a whole separate phase or is part of melting. For it to be its own phase, you would have to be able to hold it there. There would have to be a stable region where you could, as long as you had the right pressure and temperature, it would stay in that phase. And I don't think that this exclusion zone that they're talking about, and this has only been researched in the last 5 to 7 years, this term has shown up. I don't think it's its own phase so much as it's part of melting. But I don't know that for sure. It's a very new phenomenon.
You just mentioned that there's a phase of water that meets all three. Why can't it meet two then if it can meet three?
So it's not so much that it's a different phase that it can be all three. It's that you have a solid and a liquid and a gas present at the same time. So when you put ice in your drink, you're basically, the ice is melting and it's going to stay at this line until it finishes melting. So you have both liquid water and solid water present in the same system. But that doesn't mean that that mixing them together makes it a separate thing. It's still the two components.
Right.
But I guess it depends a little bit on your definition of phase, and that's probably what these papers are hashing out. They're looking at the molecular level, what's happening, and can we call that a separate phase? A lot of it depends on what's our definition, right? So they're hashing all that out, and we'll see where it comes from. At this point, they haven't convinced me, but as the saying goes, new theories do not become more popular with old scientists. Old scientists just die. So it's also possible that that'll be the conventional knowledge in 50 years. And I'll be the crotchety old man saying, well, in my day, we only had 4 phases and we liked it. It's also related to, I guess it was a little foggy over Thanksgiving break around here. I was really foggy in the valley. I was driving on Saturday morning at the beginning of break. It was super foggy. And so fog is basically, it's basically the transition, fog forming and dew and cloud formation is basically a transition where at a certain temperature, if you drop, or sorry, at a certain pressure, if you drop the temperature, you cause a phase change. If you do that to a solution, which is basically what you have when you have moisture dissolved in the atmosphere, you have a situation where as you drop the temperature, the water gets less soluble in the air. Relative humidity is not the same when you change temperatures. Hot air can hold more water than cold air can. So if you have a set amount of water in the air and then your temperature drops, that water can no longer stay dissolved in the air. And so it condenses. You get cloud formation or you get dew on the surface. If it's low enough pressure, we don't have dew formation very much up here, right? We have a lot more frost formation. It's not just because it's colder here. It's also because our atmospheric pressure is lower here. And so it's a lot easier for water to do this transition when you're at a lower pressure. And that's frost formation now. So when fog forms, we're doing this. And that's why fog typically happens, is more common in humid areas with higher pressures, closer to sea level. We see that a lot less because we get snow and frost formation instead.
Is that why every time it rains, you just know it's going to hail?
I would have to look at that. I don't know enough about meteorology. All I know about hail is that it's liquid water that refreezes on its way down. So it falls as rain and then refreezes at some point on its way down, but I don't know enough about whether our conditions, we're still really close to normal sea level. We're about 80% of the pressure of sea level, which is not very, like the upper atmosphere where cloud formation happens, we're talking more like 40% of atmospheric pressure. So we're not that far off. So I would hesitate to say whether hail formation around here is related to that. It's probably more just the type of moisture we get coming off of the delta and the ocean causes that to happen. But I don't know that for sure.
Not every time, but it's almost every
We do get a lot of hail here, although they get a lot of hail everywhere that gets a lot of rain. If you've ever spent any time in the upper Midwest in the summer, hail's like once a week, it feels like, and it rains every day.
No, I go
And if it's and tornadoes can make hail about the size of like apples.
You can, I think the record is something along the size of a softball.
Yeah.
So, if you do live in one of those areas, you have to make sure that hail damage is covered on your car insurance. And then they just come around and the insurance agents just go from door to door basically after a big hailstorm in the Midwest. And all right, here's your claim form, fill this out, answer some questions, we'll send you a check. They don't even fight it. You don't even have to make the claim yourself. They just know that they're going to be paying for it. All right, let's talk a little bit more about solutions just because we never officially defined these, and we're talking about concentration a little bit now. Solution is just anytime you've got a mixture, a homogeneous mixture of more than one component. So a mixture just means you have more than one compound present. And it can be in variable amounts. that's what separated a mixture from a compound, right? A compound is something where you had elements mixed together, but they always had to be in the same whole number ratio, right? You can't have, it's not, H2O is not, well, 2 waters plus or minus a tenth of a, or 2 hydrogens plus or minus a tenth of a hydrogen, right? It has to be in this exact ratio. But solutions mean that it's a mixture, meaning you can vary how much you have of your components. Whatever you have the most of is called the solvent. It's what's doing the dissolving. And whatever's dissolved in it is called the solute. So solute is whatever you have less of. And there are lots of different examples of solutions. We typically think of solutions as being like salt water, ocean water, where you've got salt dissolved in water. So we typically think of liquid as being, the solvent being liquid, and the solute as being a solid, but we really can have any combination of these. About the only thing, I don't think you could have a solid dissolved in a gas. I can't think of a way that could happen. But pretty much any other combination that you can think of. A solid dissolved in liquid is like salt water. A gas dissolved in liquid is carbonation, like we talked about earlier. A liquid dissolved in liquid is, we don't necessarily, in everyday life, we wouldn't necessarily think of it as being a solution. We'd think of it as just being a mixture, probably. But it is a solution. It's just, a certain ratio of 2 components. So if you have ethanol and water mixed in the right ratio, it's called vodka. Right? But it's just a solution of ethanol dissolved in water. Water is your solvent, ethanol is your solute. Right? So you can have anything dissolved in liquid. You can have gas dissolved in other gases. We look at our atmosphere, nitrogen is the largest component by about, I think it's, I always mix this up. It's either 70 or 80% of our atmosphere is nitrogen gas. Must be about 70% nitrogen, and then about 20% oxygen. And then everything else that's in our atmosphere is in that last 10%. So CO2, methane, water, argon, neon, things like that are all present in that last 10%. But that means they could all be considered solutes dissolved in nitrogen. You can even have things dissolved in solids. If you have a solid dissolved in another solid, we usually call that an alloy in terms of metals. So if you take mostly iron and you add in a little bit of chromium and a little bit of carbon, you get steel. And so it's technically a solution. We use different terms to describe it because it's not always homogeneous as well. And we've dealt with hydrates a lot. Hydrates are basically water dissolved in a solid. There's also some research that was being done a few years ago on storing hydrogen gas in a way that you lost less hydrogen. Hydrogen is such a small gas, it's really hard to store in a cylinder because it just moves right through things pretty easily. It just escapes through the metal itself. So tanks rated for helium or hydrogen are typically really thick metal to try and limit that. But they were also looking at using metals and ice at really low temperatures and dissolving hydrogen in that ice. And the ice, the crystal structure of the ice trapped the hydrogen, in theory, was supposed to try and trap the hydrogen a little bit better than just using a metal cylinder. I don't think anything practical ever came of it. But it was interesting because it's a gas dissolved into a metal. Or I think the other one they were looking at was ice as the crystal structure. All right, so there's a couple of qualitative ways we can describe solutions. If we can vary the amount of solute relative to solvent, then if we're going to describe these solutions, we need to be able to talk about it in terms of how much solute do we have relative to some other amount. So if we're trying to describe concentration qualitatively, we use terms that most of us have heard at some point in everyday life, right? Dilute versus concentrated versus saturated. Saturated just means that you've got as much as will dissolve. So that's basically if you kept adding sugar to water until it stopped dissolving and you just had sugar sitting on the bottom, that's a saturated solution of sugar dissolved in water. And that saturation point can change. If you take that same solution and you boil it, then all of a sudden raising the temperature makes solids more soluble, increases the solubility, how much you can dissolve, which is why you have to boil maple syrup. When you want it to get as much sugar dissolved in as little volume as possible, you do it at a high temperature. And then when it cools down, it's what's called a supersaturated solution. Supersaturated means you have more solute than should be allowed. And basically this happens because you need a place for a crystal to start forming. You can get more saturated than normal because you don't have a place to start making a sugar crystal. If you do this in a really really nice glass container, you can get sugar to be really, really soluble. And then when it cools back down, it'll stay dissolved until you add one little sugar crystal, or even just a piece of dust can cause a crystallization to start. And then it all basically will come out of the solution at once until it gets to that saturation point. Right, so that's what's happening with cloud formation when you see it. An airplane starting cloud formation, the airplane is flying through a part of the atmosphere that was super saturated with water, but didn't have a place to start cloud formation. The airplane just provided basically a little disturbance that allowed a cloud to start forming. It's not that the airplane caused it. Something would have caused it eventually. It was just happened to be the airplane that time. If we're going to describe numerically what concentration is, how could we do this? You guys already did a quiz that involved this, but in general terms, how would we want to, if you wanted to put numbers to, say, making salt water for boiling pasta? You make a saturated saltwater solution. You just dump, a pound of salt in your pot. Not usually. Everybody's kind of wondering just how salty that would taste. If you're trying to describe to somebody numerically so that they can boil their pasta the exact same way that you do, how would you do that?
Molarity?
Molarity is one answer. Measuring cups, teaspoons.
Low ratio of salt water.
Ratio of salt to water. Those are all basically inches.
Pinches.
Pinches, okay.
Or less than 1/8 of a teaspoon if you're being really technical.
We can, what all of these have in common is we're basically talking about an amount per volume. Right? For concentration to be uniform, we have to be talking about how much solute we have per volume of solution.
Wouldn't it be solute per solvent kind of thing? Ratio of
There are sometimes, it's not always, so sometimes it's solute relative to the total.
Okay.
Where is, I think I have that on another page coming up. So amount can be in lots of different units. The one that we used in over break on that quiz that I had to give you hey, check this out. Look at this cool unit we have. Is that we're using moles as our amount. Which makes a lot of sense in terms of chemistry, right? Because the first thing we have to do for any stoichiometry problem is whatever we have, we want it in moles. Right, so molarity, or moles of solute per liter of solution, is really convenient for chemists because it allows us to say, okay, 1 liter of this solution has this many moles. It's not as convenient for making things. If we're trying to make something in the kitchen, in the US, we measure things out in terms of volume, right? So it might be a volume for our amount divided by the volume total, or the volume of solute. Could be a one way to do it. So you could do it in terms of, you know, 1:1 ratio by volume. You do something like 1 cup of sugar for every 1 cup of water would be one way. That's the ratio for making simple syrup. You could also turn it into a percentage. You could do volume as volume of solute divided by volume total times 100. Anybody think of anything we measure that way? Who's over 21 in here?
Oh, yeah.
So
Just alcohol.
alcohol, it's ABV, right? What does BV stand for? By volume. So ABV is this. It's basically this 40% ABV. That means that if you took 1 liter of it, 400 milliliters would be ethanol, and the other 600 would be water. In Europe, and especially in the UK, they don't make solutions in the kitchen by doing volume measurements. They use mass, which is really convenient if you have a scale, because it's, you know, say, okay, take 15 grams of salt and dissolve it in 100 milliliters of water. Really easy to measure, really easy to mix it. So, you know, you can wind up with grams per volume of solvent, which is also, for the most part, volume of solvent is the same as the volume of the solution. Usually we're dealing with amounts where the extra volume of adding, say, salt to water is not going to change the overall volume of water. It turns out that when you dissolve salt in water, it actually basically fits into the empty space in between the water molecules. So your volume does not actually go up until you get to really close to the saturation point. And in fact, if you take, this is a fun experiment, it's really hard to show to a big group. But if you take 50 milliliters of water and 50 milliliters of pure ethanol, and you mix them together, you only get 96 milliliters, which is weird. Which is why a lot of times we do it in terms of volume of the solution instead of volume of the solvent, because they're not always the same. Yeah, that seems like it's contradictory, right? The mass will be the same as the two parts added together, but the volume is not. It actually gets a little bit more dense than either of them on their own.
That feels really wrong.
It does, but basically because you have attractive forces in between the different molecules, they pull each other a little bit tighter than they would normally. So the distance in between each molecule is a little bit smaller.
Guess the question to be asked is, does the pressure change?
The boiling point changes.
Does that also change the pressure?
So it turns out that pressure, the boiling point is when you heat it up to the point where the vapor pressure, which is the pressure of the liquid above the liquid. So if you have a sealed water bottle that's half filled with water, there'll be some amount of water vapor above that that's as a gas. If you change the temperature, you get more of the liquid water to be up here before it stops, before it becomes saturated. Because as you increase temperature, more liquids and solids are soluble in water, soluble in a gas. So when that vapor pressure gets to be equal to the atmospheric pressure is when you hit the boiling point. When you're at a temperature where it's spontaneously turning all of it from liquid into a gas. If you change the pressure, you change that boiling point, because you have to get to a higher temperature for your vapor pressure to be equal to atmospheric pressure, if the atmospheric pressure is higher. So that's what a pressure cooker does. And that's why things take longer to cook here. Like even just boiling dried pasta, right, takes like 1.5 times as long as the box says up here at altitude, right? Because our boiling point is not 100 Celsius. Our boiling point of water is about 94 Celsius. And that difference of 6 degrees Celsius is enough that it can really take a lot longer to boil something. to cook it fully. But if you go the opposite route, if you put it in a pressure cooker, you can get up to about 4 atmospheres of pressure, and the boiling point of water there is more like 150 Celsius. So you can cook things a lot faster in a pressure cooker because you raise the boiling point of water. Like I said, phase change is really cool stuff. All right, we're not going to practice calculating molarity right there. We're going to talk about one more concept for solutions, and this is basically just a vocab where it's barely a concept, because if we know that concentration is the amount over a volume, a dilution is just the process of lowering the concentration. Right, so it's just a specific word of saying if we want to make some things more concentrated, we call it concentrating it, which when you say it out loud sounds really dumb, right? I'm going to concentrate this. But that's actually the real term for making something more concentrated, is concentrate as a verb. You concentrate it. Realistically, if I was writing and I didn't want to be accused of being incapable of using the English language, I would say something like, you make it more concentrated. If we want to lower the concentration, it's called a dilution, though. We're making it more dilute.
And just to add more solvent.
That's one way to do it. What's the other way we could do it? If we want concentration to go down, we could make volume go up, or we could bring the amount down. So that's actually how they remove things like lead from water. Basically, you have it go through a precipitation reaction that drops the concentration of lead. Your concentration of lead in drinking water has to be below some threshold, which I want to say is like 4 parts per billion for it to be considered safe in the US. So you can do that by basically adding a bunch of pure water to it, but you still got to get pure water somewhere. Or you can remove lead by having it act in some sort of precipitation reaction. So if you have lead ions floating around in your water and you just add chloride, lead chloride doesn't dissolve in water. We learned from our lab, right? That's one of those rules. And chloride's everywhere. All you have to do is add salt to water. And what you get out the other side is you make lead chloride as a solid, which basically just means it's going to fall to the bottom of your solution, and you just dropped the concentration of lead in the water by just removing the solute.
But it's still present in the solution.
It is, but not if you filter out the solid. So basically, the next step of that is you take all of the liquid and you leave the solid behind, and then you take that solid and then you can use that to do. You basically just put it in a. You get a powder. You use it to make a dye if you're using lead-based paints, or you just put it in a container and put it in hazardous waste, or turn it back to lead metal, or sell it to chemists, or.
Does anybody even still use lead-based paints?
Not in the U.S., but there are a lot of countries in the world where they don't have OSHA and the EPA to protect consumers and citizens as much. So yes, but they shouldn't be. All right. So with that in mind, now that we've talked a little bit about solutions, a couple more really relevant quiz questions. Everybody struggled with classifying reactions. That's okay. Hopefully the lab, now that everybody's gotten through the lab, helped with that. But I also want to just reiterate, there are a lot of different ways of classifying these, like synthesis reactions versus single displacement versus double displacement. And again, my problem with these is that you can have a redox reaction that's single displacement, or you can have a complexation that's single displacement. An acid-base reaction looks a lot like a single displacement, and so does a metal redox reaction. But very different things are happening at the molecular level. So while this stuff like this is in the way that the lab presented it is helpful for understanding how to predict what to write on the other side, it doesn't really tell you what's really happening. And so since, as I mentioned before, every different field, every science class you will ever take will have its own classification of reactions based on what's relevant to that particular field, I break it down into redox and complexation because everything has to be one of those two things. It's a nice thing about flowcharts if it's all yes, no questions, right? It's either redox or it's not. Now within those, there's tons of different ways to classify them, but this at least tells us we're dealing with electrons moving around or we're just changing the arrangement of things that are already existing.
We're dealing with the first step of categorizing our reactions.
Exactly. From there, we can go lots of other ways. All right, so, and I give you some of the most common ones that show up in things like MCATs or other classes, like metal redox versus gas evolution versus combustion reaction. Combustion reactions show up everywhere because they're really common and they're relevant to both engineers and biologists. So those are some other ones that I want you to be able to recognize, but the biggest one for right now is redox versus not redox. And when I was first coming up with these slides, I was trying to find a term for not redox, and there wasn't one other than just not redox. So I came up with complexation. You're not likely to see that one anywhere else. So full disclosure, don't worry about memorizing complexation. It just means it's not moving electrons. And typically for this class is either going to be precipitation reactions or acid-base reactions. We'll add some more in third quarter, I think, that are also complexation reactions. And the reason that I settled on that name is because the other type is making what's called complex ions. So if you have, say, an iron ion dissolved in water, it actually doesn't just stay as one iron ion surrounded by water. It actually turns into this octahedral, and they call it a complex, where you basically take 6 water molecules and surround an iron ion. So you actually get something that looks like, almost like a hydrate. FeH2O6, the whole thing has a +3 charge. They call that a complex ion because it's made by making this complex by putting together all these parts and just sort of sticking them. Again, nothing's changing charge, right? So that's where that term complexation comes from. You're just assembling them in a certain way, but everything is still what it started out to be. And you can do other fun things like you do this with 6 chlorides, you wind up with a complex that looks like this. And these are 2 very different colors. So a lot of color changing chemistry is based on changing out what the ion that's dissolved in water is surrounded by.
What color is it?
This one's like it looks like, I'll try to think of an appropriate way to describe this. The urine of someone who's very dehydrated.
Okay.
It's like a sickly brown yellow.
Okay.
And this one is a lot more of a greenish yellow.
Would you see this kind of stuff like in like mine runoff? There's a lot of like irony water, you know?
Usually what's present is more water than anything else. But you can also have a mixture of these where you have like 3 waters and 3 chlorides put together to make a different complex. It'll have a different charge and a slightly different color. And so it's hard to say. It's mostly going to be water in that case, but you can also change it by doing things like mixing in ammonia, which ammonia binds to these metals a lot better than water does. And you can replace the waters with ammonia and still leave it the same color and things like that. So again, I'm getting ahead of myself. This is just, I started because I wanted you to know why I chose the term complexation and not feel like I misled you by telling you that it's, you know, universally accepted term. It's not. I won't pretend it is. It's just my best way of trying to communicate not redox.
Can you drink water that's brown like that with iron in it? That comes out of like a spring in the ground?
Iron is not typically that dangerous for you. It can cause issues long term if that's your only water. It can cause buildup in arthritis in joints. And it can cause some issues, but it's not neurotoxic like lead or mercury or anything or arsenic.
And what if you put like the mud you found at that creek spring area on your face?
Typically, things are not absorbed well through the skin, especially metal ions. The exception being metal ions that are surrounded by organic materials. Like organomercuries are way more dangerous than metallic mercury.
Don't do it if you're in a mining area.
Don't do it if you're in a mining area because all the mining tailings are pretty nasty stuff. They use a lot of cyanide and things like that.
Organomercury sounds much more dangerous. It not only is more dangerous, it sounds more dangerous than metallic mercury.
So metallic mercury, like I said, they used to give it to kids to play with. They used to line, make tooth fillings out of, a mixture of mercury and silver.
It's also what they made the first wireless game controller out of.
Really?
Yeah. Apparently.
Okay. But if you take that mercury though, if you put, so mercury 2 plus, and basically surround that with its 2 methyl groups. All of a sudden, putting organic compounds around the mercury means that it can be absorbed through your skin and it accumulates in your brain much faster and more efficiently. You actually, I can't think of who it was, some famous scientist used to eat mercury because they thought it was actually like it would cleanse things out of the body.
Isaac Newton.
Yeah, that sounds about right. He was a bit of a nut by the end of his life. So you can do that for a long period of time without having negative effects. But there was a researcher, a chemistry researcher in, I want to say Cornell, somewhere in the Northeast, that was using organic mercury and got a drop on her skin right above her glove. And didn't even notice it at the time, and she was dead 2 weeks later. Just 1 drop on her skin, but because it had all the carbons around it, it moved through your cell membranes a lot better. And your brain accumulates mercury in a certain spot of your brain that can cause brain damage and eventually death. So even though it was a much smaller amount, it's much more what they call bioavailable in terms of being able to be incorporated into the body a lot more readily because it had carbons attached to it.
Is there like a quick strip test for this that you could just like put on the mud? I have so many hippie friends.
So most aquarium stores will sell testing kits that'll have a little strip with about 5 different dots on it. Dip that in water and then watch the color change and compare it to a scale. And you can say, okay, the pH is about this. It's got about this much nitrate, this much ammonia. If you go to probably a pool store, would have one that's more centered around chlorine and chlorates. Aquarium's going to be centered around phosphates and nitrogen. If you're looking for heavy metals, I don't know where you would get that. You could probably get them online though.
Then you can get copper from aquariums.
Yeah, copper testing kits.
I mean, everything's on the internet.
Yeah, and you can get a lot of stuff on the internet. All right, if we want to use these concentration units to do something useful when it comes to stoichiometry, before we get into this, we'll come back from break doing this. Let's go through quiz 1 first. And again, I realized that the numbering got all messed up. That's the one I want. On the quizzes, I think I got it all fixed. So apologies for any confusion. Nope, I said first quiz. It's really hard to do this backwards on a track.
Still got the screen right there, no?
No, I have a screen extended so I can see other things over here. So duplicating the screen is less efficient, although you wouldn't know it by looking at me right now. All right, so when we comes to classifying these reactions, balancing the reaction, you guys all know how to do that. Even if you messed up on the quiz, you guys understand what's going on and what you're supposed to do. For these ones, it will always be either redox or not redox, right? So you can always pick one of these two. And on the test, when I'm asking you to classify reactions, if you're not sure about whether it's acid, base, or precipitation, at the very least you can say not redox, right? So it's not quite as specific, but it's still a valid way of showing me that you understand how to tell the difference. So acid-base reactions and precipitation reactions are always going to be this complexation. And some of you might not have realized it was a select all questions. So it's one of these two and then one of these as well. Right, and the most common redox reactions are metal redox reactions, where you've got a metal atom changing charge, and combustion, which is, we know what combustion is now, right? Make CO2 and water. Start with carbon plus oxygen. So those ones should be really easy to recognize. Just know that they're also redox reactions. And gas evolution reactions, like the one I talked about, like our baking soda volcano, that's not a redox reaction. So I don't like to classify, I don't like gas evolution reactions because maybe they're redox, maybe they're not. It could be an acid-base reaction in some sort of phase change happening, or it could be making hydrogen gas. And those are very different processes. So metal redox and combustion are the ones I'm most interested in you paying attention to. Acid, base, and precipitation are going to be complexation. So for this one, precipitation is going to be anytime you've got all the same stuff on both sides, we just made a solid, or a solid ionic compound. So if you start by mixing together ionic solution, a solution of an ionic compound, and another solution of an ionic compound, and you still have all of the same ions on this side, but you made a solid, that's precipitation. So again, that one should get pretty easy to recognize as well, because it's always the same thing. Mix two aqueous things and you make a solid, and all the same pieces are on both sides. Right? It's oxalate here, and it's still oxalate. It's just attached to barium, therefore it doesn't dissolve anymore. And you can definitely do process of elimination with these. Like, okay, well, I know it's redox because I can look at oxidation states and I can say it's changing. And I know it's not combustion. So metal redox is my other common choice, right? Or just leave it at redox. If it's not redox, because you can look at everything and see the same oxidation states on both sides, but it's not precipitation, at this point, the only other choice you have is acid-base. Right, so acid-base reactions can be a little bit harder to recognize, but you can always do it by process of elimination. Learn to recognize the easy ones, and that at least improves your chances, even if you're just guessing at the end. It's a 1 in 2 chance instead of a 1 in 4, right? Also a test-taking strategy when it comes to standardized tests. Anytime you can, even if you're penalized for a wrong answer, the way that they balance it, at least when I was taking the SATs, was you can eliminate 1 out of the 5 choices. Statistically, it's in your best interest to guess. You can't eliminate any of them. You should leave it blank. But that was back, I'm not sure if they still penalize you for wrong answers on standardized tests. I don't think so anymore. But either way, when you can eliminate a wrong answer, you improve your odds of guessing correctly. In this case, we've got aluminum by itself, oxidation state of 0, and we're making iron, oxidation state of 0. In fact, we have 2 metals with their charges changing. Iron is +3 over here, and now it's neutral. Aluminum's neutral, and now it's +3.
Metal redox?
Metal redox. These ones, again, pretty easy to recognize if it's all metals. Right? And even if not both of them are metals, even if one of them is hydrogen gas or oxygen gas, if you can, as soon as you can look at it and see this metal is changing charge, boom, metal redox, done. Right? You don't have to be able to identify everything to get the answer. And even when it's something like this where you don't have water involved, ammonia going to ammonium or vice versa is always the same with an extra H plus added or taken away, right? And for acids and bases, that's what we're looking for. We're looking for if we can say, okay, well, that's the same oxidation state on that nitrogen, but it's got an extra H plus. So I guess more accurately than saying the charges don't change, the oxidation states don't change on an acid-base reaction. Ammonium has a +1 and ammonia is neutral, but nitrogen is -3 in both cases. So the nitrogen's oxidation state doesn't change. And perchloric acid turns into chlorate because it loses an H plus. Anytime you've got an acid on one side and it's no longer an acid because it lost an H plus, that's a good clue it's acid base. Now, if you have an acid on this side and it turns into hydrogen gas, that's different because that's H plus turning to H, just neutral hydrogen, right? Now you're changing oxidation states. Now it's some form of redox. But when you can look at the pieces and say nothing changed charge, no atom changed oxidation state, to be more accurate, we just moved an H plus from one thing to another, it's always acid base. And those are the 4 categories I'm most worried about you guys understanding. And really, if I'm picking one thing that I want you to understand, it's these 2, complexation versus redox.
That's 2 things.
No, it's redox or not redox.
There you go.
All right, last, and then we can all recognize combustion by now. Lots of practice, right? If there's anything else present, I don't think I'm going to give you any of these, but if you happen to be burning something that had a different element present, you're just going to make some other oxide, nitrogen trioxide, nitrogen dioxide, or sulfur trioxide, or whatever else you have mixed in here is going to turn into another oxide product over here, but I'm not going to test you on that right now. For now, you can just pay attention to complete combustion means everything turns to CO2 or water. And then this was still hard because vocabulary is tricky for these. But
Na is neither.
so anytime, how did you get to that conclusion?
It doesn't change.
Bingo. So anytime it doesn't change, how come my scrolling is not working? Am I zooming? All right. So second, you can look at something and say it's the same oxidation state on both sides. That's neither, it's not being oxidized or reduced. So it's not part of the reaction really. It's what we call a spectator ion. Right? A spectator ion is all the things that we would leave off if we were writing the net ionic equation.
And chlorine lost an electron, so that means it was oxidized. That means chlorine is the reducing agent.
So which chlorine?
The aqueous. Well, yes, that
Chloride.
one. Yes.
So we have chloride and hypochlorite, right? It's one of the reasons why we don't cover this before we do polyatomic ions, so we can tell the difference. So chloride is going from -1, and the only chlorine on the product side is neutral. So the chloride is being oxidized.
Yes. Meaning that it's the reducing agent.
Meaning it's reducing whatever we put it with. So it's the
Wow, this vocabulary is clunky and unintuitive.
It is a little bit, it takes getting used to. The reason we still do this is because if we're very careful with language and everybody follows the same rules in their chemistry classes, then it means that we can communicate very specific things with a very few amount of words. It makes it very efficient if everybody's using the same rules. Says the guy who made up the word complexation.
Making up words earlier.
Hydrogen's not changing, right? It goes from +1 here. We have water, all of the hydrogen is in the form of water over here. The oxidation state on the hydrogen is still +1, right?
Hydrogen would be neither.
So hydrogen's going to be neither.
Meaning that by process of elimination, CLO must be the oxidizing agent.
You can do process of elimination, or
And
since we're
also
doing this on the board, we might as well do
oxygen.
one better. And let's show it. So again, the only product that has chlorine is Cl2. So if our oxidation state on chlorine when it's hypochlorite, oxygen's more electronegative than everything but fluorine, right? So oxygen still gets its due first. So oxygen is -2, which makes the chlorine +1. So we need our oxidation states to add up to the overall charge on the ion. If it's an ionic, if it's a polyatomic ion, our rules for oxidation states don't change. It just means we're not trying to make it add up to 0. We're trying to make it add up to whatever the charge is on the ion. So if we go from +1 to 0, that chlorine is being reduced, which makes it the oxidizing agent. And this reaction is why you never mix cleaning products or drain cleaners. Because sodium hypochlorite is bleach, and it's also found in some forms of liquid plumber. And HCl is also liquid plumber, different brand or different style. There's acidic drain cleaner and non-acidic drain cleaner. If you mix the two, you make chlorine gas and a whole lot of heat. So it boils it off really, really quickly and has the potential to cause a geyser coming out of the drain you're trying to clean. And so really easy to do with things you buy at the hardware store without even thinking twice about it, or probably things that are under your sink
You can make
together
it
already.
by accident.
You can, exactly. It's not that hard to do something that could potentially seriously injure you for a long time, or kill you. My worst experience ever in a lab, I was not making, go ahead.
Super sorry to interrupt you. On my test, this answer 2, that the oh, never mind, I'm an idiot, I told you.
No problem. I could have just as easily done it backwards too, but I've got you guys to call me on it, so I'm less likely to let that slide on my own self. I was not making chlorine gas unintentionally. Somebody left. That was my first job, was washing dishes in the chemistry stockroom. My first chemistry job, and somebody left a vial of liquid bromine, just pure liquid bromine, on the counter, which usually means please clean this. So not knowing what it was, I just opened it and dumped it into the hot water in the sink. It hit the hot water, immediately vaporized. I got a big lung full of pure bromine, and it took me about a month and a half before I could walk up a flight of stairs without stopping for a break, because it wrecked my lungs and my esophagus.
Did it cause any long-lasting damage?
Probably not, but it's chemical burns are like regular burns. If you give them enough chance to heal, it's usually okay. It was not pleasant though, so I highly recommend avoiding that. All right, let's take a break and we'll come back. We'll do practice with stoichiometry and we'll talk about pressure. So let's come back at 1/4 after. Yes, thanks. I think we said, well, so I'm of two minds about it. I could also just do it just on the test, on the final test. We'll probably just do that since we're getting short on time.
And is it just on naming acids?
It'll be on naming everything.
So
So,
like that one ICA.
like the
we
last
did,
page, that
is the
ICA.
the last page.
Right.
And so study that.
Yeah, so it'll be just like that. I won't tell you if it's an acid, base, or ionic.
Okay.
You have to look at it and know from the name or from the formula, and then use the right naming system.
Yeah, there's places like, I lived in.
We did, that's what I've done in the past, but I also covered this material in a slightly different order, and so it was more closer to midterm that we did that. This close to the final, I don't really want to take time in class, and so we can just do it on the final. Just one of the 10 parts of the final will be nomenclature. And it'll be presented just like that last page.
Yeah, that's why I really
It's a-
started to get it.
It's a bear, but when you make through it, it really kind of cements, okay, there's no way I could mess this up because I've done so much of it.
Right.
Like there was a bunch of dirt around to make like a pedal for it, so that it could evaporate instead of going into the stone. So, and then there's like places where there's like place and that's like in these pools, and it's just like you gotta like know what's around, like where you are. But also I don't know, like it's probably pretty cool. Yeah, there's anything down in there.
I didn't take point off because that one is good enough, and that one's close to it.
Some of them got really nasty.
That could be an eye in my handwriting anyways,
But,
though.
like, I found this string one time that.
But now you're gonna remember it, because even if I didn't take off a point,
And so
I made you think about it.
and it was like sticking out underneath the rock. So I was like, oh, it's really interesting. It's like a big rock, or like something on earth, you know, like it's like six through the gravel and the smoke and the clay or whatever, and that's probably. But because I know that it's probably an underground livestock that is actually like closed off. It's just draining out, you know? So like there's certain things, especially when
That's not how my teachers taught me. I'm gonna go back to high my standard.
But, and so I probably only want to go on that one.
And still you want to
Like
walk
more of a
around.
straight line.
Yes.
Like I would recommend
And
anything
minus
else.
40 water.
So like
You're the only one who was, one of them,
make sure there's
if the other one was straighter, I would have taken this one and both of them, but because this one is for me now.
As if there's
I allowed
something scooping in your water, that's just as bad. Maybe not just
You also
bad,
have
but
the
you
mixed
have,
blessing
like,
of being at the beginning of the alphabet. So sometimes I haven't fully established what my criteria is when I get to B, which can be a negative thing or a positive thing, so.
Yeah, so you get it, you don't wanna mess around with that either. I don't know, good reason not to drink out of springs unless maybe if you've had a lot of experience there, then your whole life or something. But like people, like there's springs I drink out of because I just always have. Since I was a kid, like other people did too.
If it's really well documented as well, there's a natural spring where my,
The girl I'm talking about, no, she probably didn't even look around for animal excrement.
and that
She believes.
it'll turn out okay.
It should probably be okay, you know?
Yeah,
I have Giardia.
Yeah.
Yeah, I've seen people get Giardia from doing it, like, around in the woods. And it's like, that's why I don't do it, because it looks awful.
you boil it,
It's
it's okay.
for the rest of your life. It's a little parasite.
Yeah, I know a guy who goes around drinking all of the wild live water you can find. He's like, yeah, I've already got like, 20 streams of Giardia, so like now you can drink out of any stream. I'm just like, okay, I'm not sure if that's how that works, but whatever.
In the Boy Scouts, they used to call it beaver fever. The beavers were peeing upstream for where you're drinking, didn't sit well. I'm not sure if it was full on Giardia, but
Yeah, you would get the kills you shit.
yeah. That's, historically, that's the way most people in history have died, is very unpleasant, but yeah, pretty much literally shitting yourself to death.
No idea. 11 and around 12.
It'll be a 13 pound soccer. It'll be a 13 pound soccer.
It looks like it'll fit. I feel like that sock would fit Brittany and he's a leather.
Socks are not that critical that you get the size right. It's just got to be close.
I have plenty of socks in my day, and I can tell you it has to be right.
The less stretchy.
Maybe I just haven't. I've never gotten good socks, I guess.
You have like handmade socks, they might not be as stretchy as commercial socks. You gotta make sure to fit them right.
That would make sense. A little bit. No elastic and no.
Unless you're like using elastic, yeah. Yeah, like most people probably.
This part is elastic, it's got 25%. Sorry, this is whoa.
Yeah. How long did you make your stock?
Here, this one took me 25
Days?
of free time.
Right, just like when you're doing something.
But it's like,
Oh yeah, that's a fancy sock.
this sock took me like 3 weeks to get here. Go. Yeah, I've been meaning to go look at their frames just to get, but I need to, I haven't had my eyes checked. Can you just like take them, tell them what your script is? Yeah, I think I know what these are. Like it's clear, so it must still work. Shut up. But still like.
Yeah, exactly.
Yeah.
That's legit, it just cost me like 400. Yeah, like every shop is crazy.
I know, that's all.
Yeah, I was like, I'm not even starting. You should look at it.
Are you keeping it?
I love it.
I would love to get to send.
No, I mean, I'll just all make that noise. Oh, well, guess I'm gonna be fine.
Yeah. So.
I have a question.
Okay.
What is the nature of solids as far as starch? Like, why does it act like a solid when it moves?
So starch is a polymer. And polymers behave differently because a polymer means it's a big, long chain of things, of smaller molecules. So starch in particular is actually very similar to cellulose and glycogen in that it's a big, long chain of glucose molecules linked together. The thing is, if you get a whole big, long chain, they're basically a bunch of hexagons linked together. I did this backwards, but it doesn't matter for the sake of showing what's going on. So you get these big, long chains that don't behave like individual molecules anymore. All of these, you get in starches, these can be hundreds of hexagons long. Each hexagon is 6 carbons. So we're talking about giant molecules in terms of normal organic molecules, a lot smaller. And so that means when you dissolve them, there's still a lot of reaction or a lot of interaction between this chain and the chain right next to it. And so they have a lot of attractive forces pulling this chain in both these directions, kind of making it stick together. And when you do something like push on it really quickly, you basically don't give these chains a chance to move out of the way. It's the equivalent of basically throwing a baseball at 100 miles an hour into a crowd of people versus rolling a bowling ball at 5 miles an hour. Everybody that sees it will just step out of the way if you go slow, right? If you throw it 100 miles an hour, nobody's moving out of the way. So it behaves like a non-Newtonian fluid because all of these interactions hold it really tightly together, and it takes time for them to move out of the way of force. you actually have to push through this in order to make it move. And it will move just very slowly as all of these polymers line up and arrange themselves. But it's not easy. And starch is really common, it's really cheap, and it's really easy to find. You could, if you had purified cellulose, you could, in a powdered form, you could probably do the same thing with cellulose. Cellulose basically is basically you link it at a different carbon on each of these, and it makes it cellulose. Our body can digest starch, but it doesn't have enzymes that can break down cellulose just because it's attached, say, at this carbon instead of that carbon. Right. So it's not the only non-Newtonian fluid, but it's the most common one. It's one you can make at home really easily. So it's the one most people know about. And that's really all it is with molecules that big that are that nested together, you have to give them time to move out of the way, or they behave like a solid.
Okay, I bought this potato at Whole Foods, called Japanese sweet potato, and that young thing is so starchy. I went to cut it in half, and slices like flaked off of it, like broke off of it.
So that's, I don't know the crystal structure of starch when it's solid, but it probably forms like nice nested things like that. So slicing it, if you're slicing with the grain of, if it's that starchy, slicing one direction is more likely to cause it to break apart versus the other direction. You might have been able to slice it a lot easier without it doing that. Be difficult to say that, but it's like with gemstones, you have to cut it along at the right angle relative to where the crystal structure is, and basically you're just causing it to break in a predictable way, as opposed to if you did it 90 degrees to that, you might cause the whole thing to shatter. You're not going to do that with starch in with cells, but you could. It would behave very, very similarly in terms of slicing at the right angle in the right direction. Probably would have changed how it behaved when you get to extremes like that. All right, let's do a quick practice problem. This is pretty similar to what was on the quiz. And when I'm focusing on stoichiometry problems, a lot of times I'll leave off the phases. That's not technically the most correct way to do it, but it's a lot faster when you're typing these out. So apologies that I didn't put the phases in there, but I'm not asking what the reaction type is, so it's not all that relevant. For a stoichiometry problem, we mainly care about how much of something we can make, what's the limiting reactant, what's left over. And if I'm remembering correctly, I think I did this wrong. Let's make this 0.7 molar instead of 0.5 molar, because I want to make sure we run out of the other one first. We still would want to show which one is the limiting reactant, and there's two ways we can do it. First things first, though, we want to get everything in moles. So for the one that's a solid, where you're given grams, if I don't write solid, but I give you grams, you can assume that it's pure substance. We're talking about a solid here. If we know that it's pure substance and we know we have a starting mass, we just use the molecular weight. We know what it is. So magnesium 24.305 and hydroxide is 17, so 17 and 17 is 34, and what did I say, magnesium 24.3. So what are we looking at? Something about 60? Did I do that right? 34 and 24 is 58. 0.4-ish. Feel free to correct me or add sig figs. Well, you have your calculators out. I'm doing this in my head. I think I'm close. No, 60, 34, and 24. No, 58, yeah. Or 3 sig figs, that's good enough. So we'll just stop there and say, okay, that gets me into moles. So roughly a sixth, so about 60.164. That's, oh, we're using it 2 to 1. Yeah, I definitely need more of that. Let's do 16388. So we only have 4 sig figs here, so we'll just keep 4 there. 3 sig figs. I can do mental arithmetic, but asking me to count is a lot.
Are we going with 0.7?
Oh, was that the more accurate one? Sorry.
No, for HCl. I'm asking.
Yeah, 500 milliliters at 0.7. So if we have a solution and a concentration, it looks a lot like doing a density conversion. We're going to use this concentration as a conversion to get from liters into moles. Right, so because 0. We'll add another sig fig for the sake of not rounding off our important numbers. If that is capital M, that's the same as moles per liter, 1 liter of solution. All right, so if we want to know how many moles of HCl we have, well, we've got 500 milliliters. And if we can get to liters, we can use this conversion to cancel out liters and be left in moles. So we're just going to switch it to 10 to the 3 milliliters. 1,000 milliliters is 1 liter. And then we can use our concentration in molarity to cancel out liters and be left in moles. So 0.35. All right, and if we're trying to, if we don't have it already set up the way that I tend to set these problems up, if this is a word problem, a lot of times you might see a solution where, and then it'll be written as, because if we're talking about molarity, a lot of times you have to specify molarity of what, because you can have more than one thing dissolved in a solution at a time. So we specify what we're talking about by putting it in brackets. Square brackets around the formula means we're talking about molarity. So we would write it as, we write it like that, say molarity of HCl is 0.700 moles per liter. In the abbreviated form of moles per liter, when we're saying it out loud, is molar, like a tube. So we'd say it's 0.700 molar. And this is one where, again, capitalization matters, because a lowercase m as a unit would mean meters. And actually, even as a concentration, a lowercase m means a really weird esoteric unit that is moles of something per kilogram of solvent instead of per liter of solvent, which doesn't get used all that much, but it is an existing unit for a concentration that's a lowercase m. We want to be very specific, make an uppercase m. The other one that I see is people saying that capital M is the same as moles. That's going to lead you down bad paths. That's a gateway drug to mislabeling everything. You're never going to get the right answer.
What do you mean it's not the same? Opens the molar solution?
So it's moles per liter, but you can't just say capital M is moles because it's moles per what? If you only have half a liter of it, you don't actually have 0.7 moles. You really have 0.35 moles. Right? So it's a ratio. It's a difference between a mass and a density, right?
If you got a liter of it, it would be the same.
If you had a liter of it, it would be the same. You'd have 1 mole, or you'd have however many moles of concentration you had because you had 1 liter. So just be, I would just making a note to be careful of the notation more than anything. And again, as I stopped to talk, I forgot to finish writing my units. So now that we have everything in moles, if we want to know what's going to run out first, there's a couple ways we can do it. But since the next question is asking us how many grams of magnesium chloride we could make, we might as well just see, okay, if I use all of this, how much magnesium chloride could I make? If I use all of the HCl, how much magnesium chloride could I make? And then how do we know which is the right answer? Yeah, if I have enough patties to make 10 hamburgers and enough buns to make 25 hamburgers, I can still only make 10 hamburgers, right? Whichever one runs out first dictates when you stop. So we can say, okay, well, 0.164 moles of magnesium hydroxide. And every time I use 1 mole of magnesium hydroxide, that makes 1 mole magnesium chloride. So 1 to 1, so we get 0.164 moles of product. And this should all be pretty reviewed. The only new piece of this really is using molarity as a conversion, right? If we have moles of HCl, now it's not a 1-to-1 ratio, so we have to be careful because it's 2 moles of HCl to make 1 mole of product. I believe that half of 35 is 17.5, right? Okay. So that tells us which of these runs out first. To answer these questions, this one is not a number answer, right? When I say what reactant runs out first or what's the limiting reactant, it's just tell me which compound is going to run out first. So we answered both of these at the same time. Well, not quite. We haven't gotten to grams yet. But the first step, we can say, okay, well, this must be the limiting reactant, or not really magnesium chloride. If I use all of that up, I make less product. Therefore, that's what's running out first. Now it's just moles to grams. To answer the rest of the question, how many grams will be produced? Well, for every 1 mole of magnesium chloride,
95.234.
thank you.
15.6.
Right, so the stoichiometry takes getting used to, when it's abstract chemicals, it takes getting used to what's the logics being used versus being produced, what's running out first. The concepts in the math are just as simple as with hamburgers, right?
John, I'm sorry, where'd you get the 95.234 grams?
Adding up the mass of magnesium, which is 24.3, and 2 chlorines, which are each 35.5 roughly. It just went really fast because somebody had it ready to go. If we want to know the concentration of HCl after the reaction, we started with a concentration of 0.70 moles per liter. If we want to know the concentration that left over, we need to know how many moles of HCl are excess. And then to turn it into a concentration, we just take how many moles we have and divide by our volume. Right, so if we want to know concentration of HCl final, we need to know moles of HCl. Lowercase n is the variable for moles. And volume final. When we think about realistically what we're doing here, we have half a liter of solution, we're adding 10 grams of magnesium hydroxide to it. What's happening to the volume within sig figs? Is it going to be changing? Not really. So maybe very barely, but remember, so until we get up close to the saturation point, and I don't expect you to have that all memorized, but until we're talking about like equal grams of solute to solvent, then we're going to assume that the volume doesn't really change when we dissolve a solid in it. And so if we were talking about 500 grams of sugar being dissolved in half a liter, then saying the volume's the same before and after might not be a good assumption. But when we're talking about 10 grams dissolving in 100 grams and 500 grams of water, that's a big enough gap. We can basically just say the volume's not changing. And if you're ever not sure what to do, if you're not sure if that's a good assumption, make a note that you're making that assumption, then do it anyway. I'm not sure how to answer this, so I'm going to do it the way I know how, which is to assume the volume is constant. You don't have to say you don't know what you're doing. Just say, assuming volume is constant, V final is 500 milliliters. You can make a lot of assumptions in science classes as long as you tell me what they are. Then you might be doing it right, or you at the very least can get good partial credit for it, right? Know that you're making the assumption and document it. And then I can't really fault you too much unless there was a better way to do it.
How much credit do we get for doing the non-thing correctly?
It depends on how wrong it is. If it was something like you figured out how many grams of water you made instead of how many grams of magnesium chloride, it's still the same calculation, right? Just making something different. That's going to be close to full credit. If I ask you how many grams of magnesium chloride you're going to make and you figure out the solubility of magnesium chloride in water, that's what does that have to do with the price of tea in China?
What's that? Is that an N up there? Over there in the black ink.
Where you're saying moles.
HCl final.
HCl final.
That n is moles of that.
Yes, that's a lowercase n.
It's just a variable saying moles of.
Okay.
So just like lowercase m is a variable means
It's just
mass.
so big, it was weirding me out.
Sorry.
I mean,
Sorry,
I'm not used to seeing lowercase n's that big. I don't know.
You probably haven't dealt with lowercase n as a variable since you first learned algebra, right? Even before they introduced x, for some reason they use n to represent number, I guess. They couldn't use m in chemistry because m was already mass. And we had enough variables that start with, and units that start with m. So they just went with n for number of molecules, basically. Capital N means number of atoms. Lowercase n means moles of. All right, so we want to know the concentration after the fact. We went on a big digression to say this is the same as it was before. If we're mixing two solutions, the final volume is the sum of putting them together. So if this was 500 milliliters of this solution and 200 milliliters of that solution, our final volume would be the sum of them. But if it's a solid being dissolved in a solution, we're just going to assume that the solution is not changing volume. So that's just going to be 500 milliliters or 0.500 liters, since we want it in liters. Moles of HCl final, we're just going to change this. We're still going to use our limiting reactant because that's what's controlling everything. Except now we can say for every 1 mole of magnesium hydroxide used, it's 2 moles HCl used.
Oh, pretty nice.
And so this is where having to think about it logically comes into play, because
That's the question.
if we want to know, what is the question asking? If we want to know how much is used, we just answered it. If we want to know what's left over, you take what you started with and you subtract what you used, right? And math that simple, I'm not going to tell you to memorize a formula for that. It kind of comes with understanding what subtraction is, right? And granted, it's easier when they're teaching subtraction in kindergarten, because you can say 7 cookies minus 2 cookies. How many cookies are left? With these numbers, it's not as intuitive, but it's the same process. What you started with minus what you used. Right, so our moles of HCl final
0.022.
0.022. We lose a sig fig because when we're doing subtraction, we have to keep our digits the same, right? Keep our uncertainty in the same place. And that's moles of HCl left, or excess, or however you want to describe it. Final.
Still not that. This is also the concentration.
It's still asking the concentration. So this is moles of excess reactant. If you want to know the concentration of excess reactant, we just plug it into our molarity, which is just moles of something divided by volume. So 0.022 moles of HCl in half of a liter.
0.044 molar.
So this should feel like, if I'm going to liken this to learning a foreign language, we didn't add any new verb tenses or anything. You just learned some new vocab. You learned the vocab for going to the pool instead of going to the shop, right? We now have 2 different ways we can get to moles, or where we can take moles and turn it into a measurable unit like mass or concentration. Right? All we did was we added one more way of describing the number of moles, the amount of product or the amount of reactant we have. That's all molarity is. To use another cooking analogy, you can say, I put half a pound of sugar in this cake recipe. That's probably too much. You put half a pound of sugar in this cake recipe, or you can say, I made the concentration of sugar 32 grams per cup, right? One's talking about an amount, one's talking about a concentration. But they're both ways that you could get to total amount of sugar, right? Just from different sides. That's all this is. And that's basically is how we're going to approach gases for now, until you start talking about phase changes and phase diagrams. We're going to talk about gases more or less the same way. We're going to use gases, basically if we explain some things about gases, we can add one more way to get to moles of something. So now if we have a solid or a liquid, we can get from grams to moles. If we have a solution, we can get from a volume and a concentration, we can get to moles. With gases, we need to describe them in units that we're used to measuring gases in. So, if we want to know, if we're talking about solids or liquids, all we really need is grams, because we can weigh that directly, and the density doesn't change. So you can basically measure a volume of something and use the density to figure out grams pretty easily, because it's always the same. The density of gold is the same no matter what. However, gases can change volume, which means they behave more like a solution than they do like a pure substance. because if you change the concentration of a gas, that changes how many moles of gas you have in that set volume. Right? So if gases are going to be different than solids and liquids, but they're going to be pretty similar solutions, but we're going to measure it in different variables. All right, so and the first one we're going to look at is pressure. All right, so pressure it's a physics way of describing things. It's basically a way of measuring the total force that's exerted on a surface that's due to gas molecules bouncing into that surface. Gas molecules are constantly flying in all directions, and they're constantly colliding with the barrier, with the boundaries of their container. All of that colliding means that when they bounce off of something, that wall has to push back to get them to change direction. Right? If you think about throwing a bouncy ball against the wall, the bouncy ball pushes on the wall, but the wall pushes the bouncy ball as well, right? Think of gases as basically a mole of bouncy balls, all hitting the insides of the container at the same time. You add up all of that force and put it together and divide by the area, that's pressure. And another way to think about it is the difference between this is if you think about taking dough, bread dough, if you push on it with all of your weight, it flattens out, right? That's putting whatever your body weight is over the area of your hands. If you take the same force, your whole body weight, and you put it on a smaller area, like say the area of a knife or your finger, it acts very differently, right? You didn't change the force, all you changed was the area that the force was acting on. Use the bouncy ball analogy again. If I had somebody stand up here and I threw a bouncy ball at them, repeatedly 100 times in a row, if I hit the same spot every time, it would probably start to hurt after a while, right? If I'm not really winging it, and you can assume I'm not Randy Johnson, then eventually, if I'm not hitting the same spot, that's going to be negligible, right? The amount of area is going to affect the force. It's not going to affect the force, it's going to affect how the force acts. Right, so if we want to increase the pressure, if we want to increase the average force per area, we can do that by either increasing the number of collisions or doing what down here? If we want pressure to go up, we could reduce the area. And the other example that my high school chemistry teacher used was, if you've ever had anybody walk on your back to give you a back massage, it feels pretty good, as long as, it depends on the total amount of force. It's a roundabout way of saying body weight. But if they do that with high heels on, it doesn't feel the same anymore, right? Or if they do that with ice skates on, it's even worse. Taking the same force over a smaller area, pressure goes up. If you get too much pressure, bad things start to happen, at least from the point of view of the massagee. All right, so the way we measure force over area is actually pretty basic. We have a couple ways of measuring force. The most common way in the US of measuring force is just pounds. Pounds, when we think of it, when we say weight, what we're really talking about is the force of gravity on something, on an object. It's related to how big that object is. So measuring pounds is really how hard you can push something. So measuring pressure in terms of taking a force and dividing by an area is the most basic way of doing this. Your units, you just wind up with pressure units that look like a force divided by an area. So pounds per square inch. Really, the better way of writing PSI is pounds per square inch. Just like MPH is not the right way to write miles per hour in a science class, right? It's miles over hours. Pounds per square inch is one way to do this. If you do this in metric units, they use pascals, which is a Newton per square meter. A Newton's a lot smaller than a pound, and a square meter is a lot bigger than a square inch. So you wind up with very different numbers. These are all atmospheric pressure. This is standard atmospheric pressure at sea level. It's 14.7 pounds per square inch, and it's 100,000 pascals. And so we don't actually report it as pascals usually because most people don't want to use scientific notation, so they do it in kilopascals. So 101.325 kilopascals is atmospheric pressure. And that's equal to 14.7 pounds per square inch. Despite what these look like, we're not going to do anything with force in this class. So I know I've always taught you anytime you see a combined unit, think, oh, that's a conversion. And it is, but since we don't actually do much with force in this class, we're not going to use it as such. You can use it to do things like, okay, well, figure out the surface area of a person's body, and you can figure out the total force due to the atmosphere on that person's body by adding up basically all of the square inches on their body at the same time. And that effectively is just using this as a conversion. But that's about the extent of it for chemistry. The other way that we use pascals is a bar is 100,000 pascals. So 1.01325 bar, which is short for barometric pressure, is equal to 101,000 kilopascals, which is equal to 14.7 psi. The other way we do this is actually just, instead of measuring a force and dividing by an area, we just say, well, we're just going to say this is the standard barometric pressure at sea level and call it 1. So 1 atmosphere of pressure is equal to 14.7 psi, is equal to 101.325 kilopascals, or 101,000 pascals. And all of these numbers are equal to each other. We use standard atmospheric pressure as basically our zero. We compare everything to that. And the other one is 760 millimeters of mercury, which is a weird unit for pressure, because that looks a lot like a length unit, right? This actually comes from the original definition of barometric pressure by a guy named Torricelli in, I want to say, Renaissance Italy, who basically made the first barometer. He basically figured out that if you take a big pool of, we started it with water, and basically you put a tube in it that's closed at one end and you let it fill up. It's equivalent to basically putting your thumb over the top of a straw and then pulling it out. The liquid in the straw stays in there and when you keep your thumb over the top, right? What Torricelli figured out is if you go high enough so that the weight of the water was equal to the atmospheric pressure, the reason it stays in the tube is because the gas molecules from the atmosphere are pushing on the surface of the water enough that it's pushing it back into the tube. If you make this tube long enough so that the force of gravity on the water in here is equal to the force of the gas molecules pushing down here, then it stops rising. You can actually do this to the point where basically you can make the tube longer, pull it out more, and the water level stays constant. So that's all a barometer is. The problem is that if you do this with water, it has to be about 30 feet long. So we needed something liquid that was way more dense than water, that also had as low a vapor pressure as possible. Because the other problem is, so if this is about 30 feet, up here in this empty space, you actually still get H2O as a gas floating around in there, because otherwise you would just have a vacuum. So we wanted something with low vapor pressure, much more dense than water, and it also had to be a liquid for this to work. And mercury fit the bill for all of those.
When you say low vapor pressure, does that mean it doesn't vaporize?
It does not vaporize easily, correct. So if you do this with mercury, standard barometric pressure is a little under a meter. 760 millimeters is how high the tube has to rise above the surface of that pool of mercury before it stops rising. So millimeters of mercury is a pressure unit. It's just a measured pressure unit. And this, we actually have a mercury barometer in the lab. In lab this week, you will measure directly what the barometric pressure is that day by looking at the height of mercury in a tube.
Does it have to be an open like that, so that
Mm-hmm.
so there's just like an open container of mercury hanging out?
You wouldn't know it to look at it, but yes. Yeah, and that's also relevant to that low vapor pressure, right? We don't want it to evaporate. We don't want people breathing it in, and we also don't want to have to, keep topping it off with mercury every week. So luckily, all of those things are true for mercury. It works out pretty well. And Torricelli, for his trouble, got a unit named after him. What were you saying?
How, like, does it vaporize at all?
Not appreciably at room temperature. Basically, you can, at normal pressure and normal temperatures, close to room temperatures, probably will still be there in 1,000 years. So we call that not evaporating for all intents and purposes. Technically it is, one molecule at a time. So Tor, for Torricelli, is the same, is literally the exact same thing as a millimeter of mercury. And so our atmospheric pressure up here is usually close to about 610 Torricelli millimeters of mercury. You can't just look up the barometric pressure. I just realized I'm over time, so let me finish this thought. You can't look up the barometric pressure because things like meteorology apps, they normalize it relative to sea level. So if we were at sea level, we could just look up what's the pressure today on a meteorology app. We can't do that up here because they take everything and they normalize it. And our normal pressure is 80% of normal. So basically our numbers will be off by 20%, which is pretty big if we just looked it up.
So the baseline isn't for us.
The baseline is not for us, not for meteorology. It's just for comparing changes in different parts of the world. All right, we'll end there, and then we'll talk about pressure in lab tomorrow, or Thursday. For tomorrow's lab is Rose and Rab. Bring a computer if you can. And Jordan.
The school has
Oh, fantastic.
my
School has provided.
my laptop is too late to apparently run Canvas.
Oh.
Run Canvas on the internet.
Yeah.
I know.
You got your money's worth out of that one, probably. I've got a tablet that's been kicking since before my son was born, and he's in 2nd grade now. So, be careful with your technology; it will last a while.
Yeah, I'm gonna go to my the SOS program.
Yeah.
And all my kids are younger than my father.
Yeah.
And they always say, "Oh, it's a cool life." And they're like, "Yeah, but it's old."
Good, just right spot.
Listen.
Can I turn this into you, Sean?
Please. Awesome.
Yeah.
Oh, Jeff, I didn't see